Okay. So let me start by introducing our speakers of today's one-word probability seminar. We have Hindy Drillick and Shalin Parekh. Hindy is gonna go first, and Hindy now is postdoc in Berkeley for the semester at the Simon's Law for Mathematical Sciences Institute, correct? And okay, it's gonna start as a postdoc NYU in 2026. And okay, it's gonna give the first part of the talk on extremal scale limits for random walks in space-time random media. And yeah, I think we can start. And let me just say that to the people attending, for any questions, just raise your hand in the Zoom, and I will unmute you. Question, please.
Okay, thank you, Federico. Thank you so much for the invitation, and thank you everybody for coming. So today I'll be talking about a series of joint works with Sayan Das, who's a postdoc at the University of Chicago, and then Shalin, who will be talking after me. So essentially, this title is a fancy way of saying that we're studying random walks in random environments. So I'm going to introduce this model. So the model that we're considering has a time-dependent random environment, which is essentially just a family of IID random variables, omega, that are indexed by time and space. So time for us is a non-negative integer, and x is also an integer. And these are random variables that take values between 0 and 1. So for example, you could think of the uniform random variable on the interval 0, 1. And we want to run a random walk in this environment. And the way that we do this is if the random walker is at position x at time t, then it will take a jump to the right with probability omega t comma x, and it will take a jump to the left with probability 1 minus omega t comma x. And of course, because the omegas take values between 0 and 1, these define probabilities. So here I wrote this out more formally. So P omega denotes this quenched probability. So in other words, it's the probability depending on omega that the random walker that's at position x at time t is at position x plus 1 or x minus 1 at time t plus 1. And these P omegas are themselves random variables because we have these two levels of randomness in our model. We have the random environment and then the random walk. We can also run k-walkers, which I would denote by R1 up to Rk. And these are k-walkers that we can run in the same random environment. I just want to point out that this is different than Sinai's random walk in random environment. So that's another popular model, but in that model, the omegas only depend on x. Whereas for us, it's important that the random environment is IID in both space and time. So the environment refreshes at every time. Okay, so this is the model, but so far we haven't really specified the distribution for the environment omega. So I just want to give several examples of what that can look like. So in all of our theorems, we're always going to assume that the expected value of omega is 1/2, so that on average, the random walks are centered. And the variance of omega will be denoted by sigma squared. So because our random variables take values between 0 and 1, the variance is necessary, and because they're centered, the variance is necessarily between 0 and 1/4. But we're going to see, we're going to exclude the case where it's equal to 1/4, and we'll see why in a second. So the most trivial example is just to take the omegas to be deterministically equal to 1/2. So this is kind of removing that second level of randomness, but this just gives us IID simple symmetric random walks, right? There's no random environment. And this corresponds to the case where sigma squared is equal to 0. On the other hand, we can take the omegas to be Bernoulli 1/2 random variables. In this case, the omegas are either 0 or 1. And if they're 1, then any random walker that's at that position will have to jump to the right. If they're 0, then the random walk has to jump to the left. So if we run a bunch of random walks in this environment, then they'll coalesce, meaning if they're, two walks are at the same position at the same time, well, then they are forced to take the same jumps from that time onward. And this is the case where sigma squared is equal to 1/4, and this is kind of a degenerate case because the random walks coalesce, so we don't want to consider this case going forward. A third interesting example is if you take the omega to be beta distributed. is called the beta random walk in random environment. And this particular choice of environment was introduced in a paper by Parekh and Corwin in 2017. The reason that this choice is interesting is because it makes the model exact in the sense that the quenched probabilities have certain exact formulas. So this model has been, more extensively studied than other choices of environment. But going forward, we're only restricting ourselves to exclude the Bernoulli case, but we're not going to, necessarily need to consider the beta case. So we can consider your favorite distribution on the interval 0, 1. Okay, so in the general case, even though the random walks don't coalesce, they still have some sticky interactions. So what I mean is that if two random walkers are at the same position at the same time, then they'll tend to stick together with higher probability than two independent random walks. And we can make this more precise by considering the following probability. What's the probability that if two random walkers are at the same position at time t, that they're still at the same position at time t plus 1? So, this can happen if both random walks jump to the right, which will happen with probability omega squared, or if both of them jump to the left, which happens with probability 1 minus omega squared. Now, this is still a quenched probability. In other words, it's still a random variable. So we can now take its expectation with respect to omega. So when I use this blackboard expectation, I mean the expectation with respect to omega. And then we see that this is equal to 1/2 plus 2 sigma squared. So in particular, as long as, sigma squared is non-zero, this is strictly larger than 1/2, meaning that the random walks have more than a 1/2 probability of sticking together. So we call this the sticky interactions between the walkers. Okay, so the main object of interest for us is the quenched probability density, or sometimes I might say the quenched heat kernel for the random walk, which is the probability that at time t, a random walker is at position x. And we're assuming that at time 0, the random walk starts at position 0. So we use this shorthand, which is p of t comma x. Now this is a random object because it still depends on omega. So it makes sense to ask about the fluctuations of this object. And it will turn out that the fluctuations are going to be governed by certain stochastic PDEs. And in particular, because we can kind of think of this as like a heat kernel for the random, the fluctuations will be given by certain stochastic heat equations. So we'll see this more precisely soon. Okay, so what does this quenched density look like? Well, I said it should kind of resemble a heat kernel. So to first order, it looks like, the Gaussian density, but it has these random fluctuations around it, which is what I'm trying to denote by this kind of squiggly curve. And the question is, what are these fluctuations? And it turns out that it depends on what regime we choose. And by regime, I mean the relationship between t and x. So there have been 3 regimes that people have studied. And the first one is the bulk regime or the diffusive regime, where you take x to t. And this is just the usual diffusive scaling for a random walk. So we expect that this, a typical particle at time t should be at a position of order square root of t. And this was first studied by Boldragini and Pellegrinotti in 2001, where they showed that in this bulk regime, the fluctuations themselves are Gaussian. And then there were, a series of papers by Balash, Rasul Aga, and Sepalainen, and also Joseph, Rasul Aga, and Sepalainen, where they showed that for a related object called the quenched mean, the fluctuations are also Gaussian. There was also a paper by Yu in 2016 that showed that for a related model called sticky Brownian motion, you have Gaussian fluctuations in this regime. So this bulk regime has been well studied. And then on the other end of the spectrum, you could go far out into the tail to the large deviation regime over here, where you take x to be of order t. So now you're asking, okay, what's the probability that the random walk in random environment is of order t at time t? And this was first studied by Parekh and Corwin, just in the context of the beta random walk in random environment, where they showed that the fluctuations in this regime are given by the Tracy-Whittam GUE distribution. If you haven't seen this distribution before, it was first discovered in the context of random matrix theory, where it was shown to govern the fluctuations of the largest eigenvalue of the Gaussian unitary ensemble. But if you haven't seen it before, the key, point right now is that this is this is a non-Gaussian distribution. So we see that somehow the fluctuations transition from being Gaussian to being non-Gaussian as we go farther out into the tail. There's also a paper by Parekh and Richnovsky where they show the Tracy-Whittem fluctuations for sticky Brownian motion, which is like a continuous version of the random walk in random environment. Okay, and the intuition here is as follows, right? So if we're looking at large deviations or rare events, then to see that, we would need to run many, many particles or many random walkers. And if we have a very large number of random walks, then they're going to have a lot of interactions with each other due to the sticky nature of the system. And the interactions will play a big role, causing this non-Gaussian behavior. Whereas if you're studying the bulk regime, you only need to look at the typical particle. So you just need to run a small number of particles. And, eventually the particles will separate and they won't really have any interaction. So the point is that the interaction really plays a larger role when you go further out into the tail behavior. So the natural question is there some intermediate scale where we see this interpolation from Gaussian to non-Gaussian behavior? And a series of physics papers by Thierry and Ledoussol conjectured that there should be a crossover from Gaussian to non-Gaussian behavior precisely in the regime where x is equal to t to the 3/4. So this is because it's in between the bulk and large deviations regimes. And they conjecture that in this regime, the fluctuations should be given by a certain stochastic PDE, namely the multiplicative stochastic heat equation. So we'll define this more precisely. That this should govern the fluctuations in this regime. There was a paper by Parekh and Ledoussol where they partially confirmed this at the level of moments for the beta random walk in random environment. So they showed that the moments of the quenched density converge to the moments of the multiplicative stochastic heat equation. But they weren't able to show the full weak convergence at the level of the process. There were also some numerical simulations by Haas, Carol Godfrey, Corwin, and Corwin that also kind of this conjecture. Okay, you could see that I also wrote KPZ here. So, we're considering the fluctuations of the quenched density P, but for some applications, it's more natural to consider the fluctuations of the logarithm of P. And we'll see later that if you take the logarithm of P, then that will be governed by another SPDE called the KPZ equation. Okay, so this is kind of the picture of the different scaling regimes. And just some terminology that will be useful. Because we have this transition from Gaussian to non-Gaussian behavior at this t to the 3/4 scale, we're going to call this scale critical. And we're going to call all smaller scales subcritical and all larger scales supercritical. So in fact, you could ask what happens for all these scales in between the bulk and the moderate deviation regime, right? What if you take t to the alpha for some other alpha in between 1/2 and 3/4, or some alpha in between 3/4 and 1? And it turns out that, okay, we'll see that for all alpha less than 3/4, we still expect Gaussian fluctuations. So we'll see this in a second. So in particular, what we're going to do in this talk is, number one, we're going to resolve the conjecture, the physics conjectures in the moderate deviation regime, and we're going to rigorously prove that the fluctuations in this regime are given by the multiplicative stochastic heat equation. So this was a work of myself, Sayan, and Shalin Parekh from 2024. Then we're going to show that for all subcritical regimes, the fluctuations are Gaussian. So they're not just Gaussian in the bulk, but they're Gaussian all the way up to the moderate deviation regime. So this is a recent result of myself and Shalin. Note that we're proving these results for all environments. So we're not restricting ourselves to the beta random walk in random environment. And then finally, this will be mainly the focus of Shalin's talk, we're going to ask what happens in higher spatial dimensions. So it makes sense to define the random walk in random environment in higher dimensions. And in higher dimensions, the kind of critical scaling will occur at a different location. So what we're going to do is identify the appropriate critical scale in higher dimensions, and then we'll be able to prove Gaussian fluctuations for the subcritical regimes in higher dimensions. So far, we haven't been able to prove the critical fluctuations in higher dimensions, but Shalin will discuss this. You can also ask what happens above the moderate deviation regime but this is still open, and I'll mention this towards the end of the talk. So this is the outline for the rest of the talk, and before we continue, I need to explain what the multiplicative stochastic heat equation and KPZ equations are. So now I'm going to give a little crash course in about the stochastic heat equation. So we can just start with the ordinary deterministic heat equation. So suppose we have the heat equation in one dimension with some forcing term h. So for now, h is just some deterministic forcing term, and our heat equation starts with initial conditions f. Then it's known that the solution to this heat equation form, where basically the first term is you just convolve the initial condition with the heat kernel, and then at every later time you need to convolve the forcing term h with the heat kernel as well and integrate those in time. So this is the solution to this forced heat equation. And the stochastic heat equation will just be the case where we take h to be stochastic. So we take a stochastic forcing term. So in particular, we'll want our forcing term to be a space-time white noise. So we're going to let C denote a Gaussian space-time white noise. In other words, it's a centered Gaussian field with delta correlations in space and time. And now our stochastic heat equation will again just be the usual deterministic heat equation, but now our forcing term will have, okay, we could have some function h, which could be deterministic or random, but now we're going to multiply that by the space-time white noise. So this is the stochastic heat equation that we're considering. But now, of course, the space-time white noise is a rough object, and it's no longer clear how to make sense of this PDE because we can't necessarily expect things to be differentiable once we multiply them with a space-time white noise. But it turns out that we can use the same Duhamel form that we saw in the previous slide to give a definition for what it means to solve the equation. So we can actually write out the Duhamel form, where now we're actually integrating against this stochastic forcing term, but we can define this to be the solution to the SPDE. So we say that U is a mild solution if it solves this integral equation given by the Duhamel principle. Now, of course, to make sense of this, we do need a notion of a stochastic integral against the space-time white noise, and this was made precise by Walsh's theory of integration against space-time white noise. And this all works out very well in one dimension, and there's, you could show existence and uniqueness of the solution under reasonable assumptions on H and F. We'll see in Shalin's talk that things get a bit more complicated when you try to do this in higher dimensions. Okay, so this is the type of SPDE that we're working with. Now, if H is a deterministic function, then we say that our stochastic heat equation has an additive noise. And in this case, the solution will be a Gaussian process because all the noise, all the randomness is coming from this Gaussian process. H is deterministic. So the solution is just an integral of something deterministic against the Gaussian process, which will still be Gaussian. On the other hand, if we take H to be a multiple of U itself, where U is the solution to the SPDE, then we say that our equation has multiplicative noise because we're multiplying the noise by the solution itself. And if we have some coefficient gamma, we call gamma the noise coefficient because it governs the strength of the noise. And in this case, with multiplicative noise, the solution is no longer Gaussian because now we're integrating something random against our space-time white noise. So the multiplicative stochastic heat equation is a very rich object, and it has many interesting and non-trivial properties. In particular, I want to point out one connection, which is what happens when we take the logarithm, because like I mentioned earlier, in some applications, it's more interesting to look at the logarithm of the thing that behaves like the multiplicative stochastic heat equation. So if we define H to be the logarithm of U, then at least formally, H will solve the following SPDE, which is called the Carter-Parisi-Zhang equation. So again, we have a heat equation component, but now we have this nonlinear term where we're taking the square of the slope of H. And finally, we have an additive noise term. Now, this equation is much more complicated than the multiplicative stochastic heat equation due to this nonlinear term, which is very difficult to make sense of because it's already difficult to make sense of what we mean by taking the derivative of these rough objects, but it's even more difficult to then define the product of these objects. So this is highly non-trivial, and Martin Heirer was able to use regularity structures to show that there is a solution theory for the KPZ equation, and the solution is actually the logarithm of u. Yeah. Okay, so this is one interesting connection, and the KPZ equation often arises to model random surface growth. So it also has a very rich behavior and is connected to many interesting physical systems. Okay, so I mentioned that the multistochastic heat equation, or the KPZ equation, is serving as this crossover between the Gaussian and Tracy-Woodham distributions. So I just want to give a brief explanation of why that's the case. So here I just wrote down the multiplicative stochastic heat equation with this multiplicative noise starting from the Dirac delta initial condition. So the claim is that this SPDE does really cross over or interpolate from the Gaussian to Tracy-Woodham behavior. So if we look at the small time behavior of the multiplicative stochastic heat equation, then somehow the dominant term to first order is just the heat kernel, because the dominant part of the equation will just be this heat equation component. So then if you if u behaves to first order like g of tx, you can just plug g of tx here in for u. And then we get that the small time behavior is given by the additive stochastic heat equation, where now instead of u, we have g here, which is just a deterministic function. And like I said before, this is a Gaussian process. So it's its 1-point distributions are Gaussian. On the other hand, the seminal paper by Amir, Corwin, and Questel showed that if you look at the long time behavior of the KPZ equation, its 1-point distribution converges to the Tracy-Woodham distribution under a certain scaling. And this is why we say that these equations cross over from Gaussian to Tracy-Woodham. Because their short time behavior is Gaussian and the long time behavior of the KPZ equation is Tracy-Woodham. So, okay, the multiplicative stochastic heat equation is the exponential of that, but essentially they cross over between these universality classes. Okay, so now I'm going to state our results where we'll see these SPDEs appearing. So even though chronologically we first proved the result in the critical fluctuations in this t to the 3/4 regime, it will be easier to state the results starting from the subcritical regimes. So our first result is actually in the bulk regime. So even though this was studied by those previous authors, the previous result by Boldraghini and Pellegrinotti in the bulk regime was just a 1-point fluctuation result. So we strengthened that to a process level result. So we're going to consider, again, any environment with these two conditions. And we're going to look at the scaling limit of our quenched density in this diffusive regime. So we're going to look at a time of order nt and a spatial position of order square root of n times x. So now n will be our scaling parameter that we take to infinity. And by a local central limit theorem, if we multiply this by square root of n, then to first order, we expect this to behave like the heat kernel. So remember that capital G is always just the usual heat kernel in one dimension. So if we subtract off the heat kernel, we can ask what the fluctuations around that look like. And it turns out that the correct thing to do is to now blow things up by n to the 1/4 so that we can see some non-trivial fluctuations. And if we can take the limit as n goes to infinity, then this scaling limit will satisfy the following additive noise stochastic heat equation. So this is, again, the stochastic heat equation. And now we have some coefficient, which I denote in red, which is just some noise coefficient that depends on sigma squared. And the noise term now is slightly more complicated than what we saw before, but it has this partial derivative in x of the heat kernel multiplied by space-time white noise. So this is the SPDE that U solves starting with 0 initial conditions. So just a few comments about this SPDE. So the first one is, since again, G is deterministic, this is still an additive noise SPDE. So this is a Gaussian process. So this really matches with and generalizes the previous results in this regime. Why do we have this partial derivative of x in front of the noise? Well, P is a probability density. So if we sum up an X over here, we expect that the total mass should be 1. So it's natural to expect that the limiting SPDE should also conserve mass, and this is why we have this partial derivative in front of the noise, which ensures that this SPDE conserves mass. And okay, I'm sweeping some technical details under the rug because what does it mean to take the limit as n goes to infinity of these objects? And it turns out that to make this convergence rigorous, we need to interpret our quenched density as a distribution that acts on spatial test functions, and then take this convergence in the space of distributions. So we'll see more about this later in my talk and also in Shalin's talk. Okay, so the next regime that we want to study are these intermediate regimes between the bulk and critical scale. So we're going to let alpha be some exponent between 1/2 and 3/4. And now we want to study the fluctuations of the quenched density in this scaling regime. So we're going to take time again to be nt, and now space will be n to the alpha t. We can also allow an additional perturbation of order square root of n times x, and it turns out this is the correct scale in which we can see non-trivial transversal fluctuations in space. But the main scaling that we're considering is this n to the alpha scale. Now, this is already pretty far out into the tail, so as n goes to infinity, this probability vanishes. So in order to actually see anything interesting, we need to multiply this by something. And in particular, we're asking that our random walks have drift n to the alpha minus 1, right? Because at time nt, we want the random walk to be at position n to the alpha t. So to see something interesting, we should exponentially tilt our random walk to add in this drift of n to the alpha minus 1. And to do so, it turns out that we should multiply it by the following deterministic prefactor, which is basically the Radon-Nikodym derivative that will tilt our random walk to give it drift n to the alpha minus 1. So in particular, we define the CNTX so that if we multiply the quench probability by this prefactor, now this does behave like the heat kernel to first order under this tilting. So now, after multiplying by this tilting, we can subtract off the heat kernel and now blow things up. It turns out the correct scale to look at is n to the 3/4 minus alpha. And now we can ask about the scaling limit of this recentered and rescaled object. So these are the next two results. So again, now V just represents the scaling limit of this object. So if alpha is strictly between 1/2 and 3/4, then V solves the following additive noise stochastic heat equation. It's basically the same stochastic heat equation as before. The only difference is that we remove the partial derivative in front of the noise term. And this is due to the fact that now we tilted by this exponential prefactor, so we no longer have conservation of mass anymore. But aside from that, this is still a Gaussian process, so the fluctuations in this regime in particular are still Gaussian. And again, we have the same noise coefficient in red, and I'm going to talk more about that in a bit. And finally, okay, so this first result was proven in the recent paper of myself and Shalin. And finally, going back in time to the case where alpha equals 3/4, well, in this case, notice that n to the 3/4 minus alpha is just 1, so we don't actually need that term. So now, okay, the GTX just converges to GTX. So actually, we can just decompose V into U minus GTX, where U is just the limit of this part. And U will now solve the multiplicative noise stochastic heat equation. So now instead of the heat kernel here, we have U here, which is the solution to the equation itself. And now we have Dirac delta initial conditions, which is just reflecting the fact that the original random walk started from 0. So we see the same initial condition for the limiting SPDE. Okay, so let me just put all three SPDEs on one slide so we can compare them. So the summary is that we showed that for alpha equals 1/2, we have this first additive noise SPDE that conserves mass. So this is a Gaussian process. If alpha is between 1/2 and 3/4, we still have Gaussian fluctuations, but with a slightly different noise term that no longer conserves the mass. And finally, if alpha is 3/4, we have truly non-Gaussian fluctuations given by the multiplicative stochastic heat equation. And notice that we have the same noise coefficient in each of the three regimes, and that this noise coefficient is somewhat non-trivial because, okay, so the numerator is basically sigma squared. And sigma squared is natural here because sigma squared is the variance of the omegas, which are like the pre-limiting noise. So it's natural that the limiting noise should also have sigma squared. So maybe really a naive guess would be just to expect sigma squared here. But in fact, we have something larger than sigma squared because we have this denominator 1 minus 4 sigma squared. So the question is, why do we have this larger noise coefficient? Where does this extra noise come from? And some of you may have seen a similar kind of noise coefficient appearing if you've seen the directed polymer model. So I just want to point out for people who've seen that in the directed polymer model, there are similar noise coefficients that appear with this form like sigma squared over 1 minus sigma squared. But in that model, these coefficients appear in higher dimensions, but not in one dimension. So what's really interesting about this model is that we're already seeing these non-trivial noise coefficients in one spatial dimension. Okay, so because of this, we actually were able to prove the following result, which we proved in the case alpha equals 3/4, which is to ask what happens if we try to keep track of the pre-limiting noise and see how it converges to the limiting space-time white noise. So we defined the following pre-limiting noise field, which is just basically the omegas on this correct moderate deviation scale. And then we just subtract 1/2 so that it's a centered noise. We need to rescale this suitably so that the variance stays order 1. But then what we proved is that if we take the joint convergence of this pre-limiting noise and the quenched density, then in the limit, while this pre-limiting noise Xi converges to a space-time white noise, which we call Xi1. But Xi1 is not the entire space-time white noise of the limiting equation. So in fact, the limiting equation has a space-time white noise that can be decomposed into two independent space-time white noises. So one of them is Xi1, which is coming from the pre-limiting noise. And the coefficient of the Xi1 term is this more naive guess of sigma squared, right? Because that's just the variance of the pre-limiting environment. But then we have an independent component, which is independent of this pre-limiting noise field. And that has this other coefficient. Now, if we take the sum of the squares of these coefficients, we do recover 8 sigma squared over 1 minus 4 sigma squared. So this is just a refinement of the previous theorem where we keep track of the contribution from the pre-limiting noise. So we call this result creation of independent noise in the limit because we can somehow see in the limit that part of the noise decouples from the pre-limiting noise. And this, makes the model pretty interesting, and it causes some complications when trying to prove these types of results. So in particular, a popular method for proving convergence to stochastic heat equations is using the method of chaos expansions. And it turns out that because of this extra noise, that method fails in this setting. So as we'll see more in Shalin's talk, we have to come up with some other proof techniques, in particular using a martingale problem formulation for these SPDEs. Okay, so note that this was for alpha equal 3/4. Actually, we should be able to prove a similar result for other alpha, but we only formally proved this for alpha equals 3/4. Okay, for the rest of the talk, I want to focus, yeah.
In the previous slide, so you expect exactly the same phenomenon, no? Also for alpha smaller than 3/4.
Sorry, I can't hear. We expect?
No, you expect the same.
For all alpha less than 3/4.
Yeah, 3/4. I mean, the same proof should go through.
Yeah, the same proof should go through. It's just that we didn't write it out in the second paper. So, but
okay.
Modulo the details, that should be true.
Okay.
Yeah. So for the rest of the talk, I want to focus on two particular aspects of the results. So of course, two natural questions are, where is this 3/4 coming from? Like, what is special about 3/4? Why is it at that scale that we see this crossover? And the second question is, where does this larger noise coefficient come from? In particular, why do we have this denominator, which makes the noise larger in the limit? And to answer both of these questions, it suffices to look at the second moment of the quench density. And through an analysis of the second moment, we can answer both of these questions. Now, to study the second moment, we first need to understand what's called the two-point motion of the system. So the two-point motion is basically just these, it's considering two random walks, R1 and R2. We run them in the same environment, but then we average out the law of the environment. So in other words, P omega was just the quench probability, but now to compute probabilities, we take an additional expectation with respect to the law of omega. So this is sometimes called the annealed measure. So we're basically looking at two random walks after averaging out the environment. And the behavior of these two random walks is the following. So when they're apart from each other, they just behave like independent, simple, symmetric random walks. But when they're at the same position at the same time, they have these sticky interactions that we discussed earlier. So in particular, I wrote out the transition probabilities here. So for example, the probability that if they're both at position y, they both jump to position y+1 is given by the expected value of omega squared. So this is a sticky interaction because, again, it's strictly larger than 1/4. Okay, so now we want to compute the second moment. And what we're actually going to do is we're going to view the quench density as a random field tested against a macroscopic spatial test function. Because I mentioned that actually to take the limits, we do need to test against spatial test functions. So in fact, this object that I'm defining here is the actual object that we're taking the limit of. So basically, it's just this object that we wrote down before, but now we integrate against the spatial test function phi. Well, we could rewrite this by just doing a change of variables and moving all the interesting rescalings into the function phi itself. And we can notice that now we're summing over x and we're multiplying by the probability that the random walk is at position x. Well, this is just an expectation with respect to the quenched probability measure. So it's just an expectation over a single random walker in the random environment. So if we want to compute the second moment of this object, well, then we're going to get an expectation with respect to the two-point motion because we are averaging out over the law of omega. But now we'll have two copies of everything. So we'll have two copies of these tilting prefactors and two copies of the random walk, each tested against phi. Okay, so because, like I said earlier, we defined these complicated prefactors C and Tx so that they exponentially tilt the random walks. Now we want to tilt R1 and R2 together. When R1 and R2 are apart, they're independent random walks. So the product of the two C and Tx terms will just exponentially tilt the pair of random walks. The problem is when the two random walks are together, they're no longer independent because of the stickiness. So if we want to tilt the random walks when they're together, we need some correction in addition to the product of the C and Tx's. So in particular, if we want to, interpret this under the tilted measure, well, we pick up this correction factor, which accounts for the times where the two random walks are intersecting. So we can look at this correction term. It's basically the exponential of the discrete intersection local time, right? So we sum up from time 0 to time nt-1, the indicator function that the two random walks are at the same position at that time. And then we multiply by the square of the drift, which is n to the alpha minus 1, and also by the variance. So this turns out to be the correct term that we get here. And so to understand the second moment, we basically need to understand this discrete intersection local time for these two random walks. So that's going to be the focus for the rest of the talk. So we have the following, so suppose R1 and R2 were just two independent, simple, symmetric random walks. Then we know that their discrete intersection local time should converge to Brownian intersection local time if we divide by square root of n. So ignoring the red term, the limit of the discrete local time converges to the local time at 0 of the difference of two independent Brownian motions. Now, because our two random walks are not independent, they actually spend more time stuck together, right? Because they have this sticky interaction. So actually, it turns out that their discrete local time converges to something larger than the Brownian local time. it converges to Brownian local time multiplied by this prefactor 1 over 1 minus 4 sigma squared. And this encapsulates the extra stickiness of these random walks and the extra time that they spend together. More formally, you can derive this 1 over 1 minus 4 sigma squared by computing the invariant measure of the random walk R1 minus R2. So this is a random walk, and it has an infinite invariant measure. Now, for a simple symmetric random walk, the invariant measure is just a counting measure. But for this sticky random walk, the invariant measure will have extra mass at 0 because the random walk will spend more time at 0. And it turns out that the extra mass at 0 is precisely this 1 over 1 minus 4 sigma squared. So already here, we can see that the arguments really depend on the dimension, because in higher dimensions, we don't have Brownian local time, right? So we're really using the dimension-dependent nature of the 1D random walk. And here we see where this denominator 1 over 1 minus 4 sigma squared comes from. Okay, so going back to what we had, we wanted an initial of this discrete intersection local time, but we had this prefactor n to the 2 alpha minus 2. And we saw that we should have 1 over square root of n if we want the discrete local time to converge to Brownian local time. Well, it turns out that we'll get 1 over square root of n precisely if we take alpha to be 3/4. So it's precisely at that scale where the discrete local time will converge to something non-trivial in the limit. And then if we take the limit of the entire second moment, well, now this exponential term will just become the exponential of Brownian local time, but with this correct noise coefficient that, the now correct noise coefficient. And under the tilted measure, these random walks, R1 minus n to the alpha t over square root of n and R2 will each converge to Brownian motions, because under the tilted measure, we've added in this drift. So the random walks are now centered and on a diffusive scale converge to Brownian motion. So this formula for the second moment is actually the Feynman-Katz representation of the second moment of the multiplicative stochastic heat equation. This is Bertini and Concrini. So we see here that it's, when alpha equals 3/4, we get the second moment of the multiplicative stochastic heat equation. We also see that if we take a larger alpha, the second moment will blow up. And if we take a smaller alpha, the local time will converge to 0. So then to actually see non-trivial fluctuations, we'll need to recenter and rescale, which is what we saw for the subcritical scaling limits. Okay, so I guess, for the last couple minutes, I just want to give a teaser of what happens in higher dimensions. And then again, Shalin will flesh this out more fully. So let's define the random walk and random environment in 2 dimensions. So in 2 dimensions, we again have an IID random environment indexed by time and space, but now space will be a vector in Z2. And now our random environment is actually a random vector. So it'll be a random vector with 4 components, and these should be non-negative components that sum up to 1. So for example, you could take the Dirichlet distribution with 4 components. So now if we're at some position x on Z2, we now have these 4 transition probabilities for jumping in each of the 4 unit directions, and they sum up to 1. So this is a valid random environment. And again, what we're going to be interested in is the quenched density for a random walk in this random environment. So we're going to look at a time of order nt, but now we want to take some spatial scaling that will be determined. So we're just going to leave it as some vector dn times t, where we want to determine what is the correct scaling for dn to see this kind of critical behavior emerge. And again, we can also take this extra diffusive transversal scaling. Okay, now this is in 2 dimensions. You could imagine defining the analogous random walk and random environment in any arbitrary dimension. So in these higher dimensions, the second moment computation will boil down to the same kind of exponential of the discrete intersection local time, but now the prefactor will be given by the drift dn over n, or the square of that drift. So the question is, what should dn be so that this converges to something non-trivial, right? We kind of want to repeat the analysis that we did in 1 dimension. Well, in D equals 2, the discrete local time of two-dimensional random walks behaves quite differently. And a classical result of Erdos and Taylor tells us that the correct rescaling is to divide by log n instead of square root of n. And if we divide by log n, then the discrete intersection local time converges to an exponential random variable. So x is an exponential random variable with rate 1. And because we have these sticky random walks, we actually need to multiply again the invariant measure at 0 of R1 minus R2. So I'm defining pi inv to be the invariant measure of this difference walk R1 minus R2. So it again represents the extra mass at 0, or the extra stickiness between these two random walks. Now, in 1D, we computed this explicitly, and it was 1 over 1 minus 4 sigma squared. Because we have more parameters and higher dimensions, it's hard to compute explicitly, but you can compute this invariant measure. Yeah, in theory at least. In D greater or equal to 3, the behavior is more different because the random walks are transient, so there are only a finite number of intersections between them. So we don't need to renormalize by anything, and it will just converge to a geometric random variable. Again, in our situation, we'll multiply by this pi inv factor. So because of this, to kind of identify the critical scale in higher dimensions, we just need to solve for dn so that dn over n is equal to the correct thing that makes this discrete local time converge. So in d equals 1, we saw that should be n to the 3/4. In d equals 2, that turns out to be n over square root of log n, right? If dn is of order n over square root of log n, then dn over n squared will be like 1 over log n, which is the correct scaling for this 2D local time. And in d greater or equal to 3, we don't need to rescale, so we want dn to just be of order n. And this makes sense because we need to go farther out into the tail in higher dimensions to see anything interesting, because in higher dimensions, the random walks don't meet up as often, and you have fewer interactions between them. Okay, but this is not enough because we're actually taking the expectation of the exponential of the local times. This is kind of like the moment generating function of the local time. And in one dimension, that's the exponential of the Brownian local time, whose moment generating function is defined everywhere on the real line. But in higher dimensions, we're getting something that looks like the moment generating function of an exponential or geometric random variable. And these moment generating functions are not defined on the entire real line, right? Like, for example, a moment generating function of an exponential of rate 1 is 1 over 1 minus t, and it blows up when t is equal to 1. So it turns out that it's not enough to just identify the order of the scale. Even within those scales, we need to consider the constant prefactors, and if they're large enough, then the second moment will still blow up. So this is an extra complication that appears in higher dimensions that makes, that adds like an extra regime, and we'll see more of this in Shalin's talk. But the main takeaway that I want to emphasize is that a lot of the analysis to identify the critical scales really can just come from doing this analysis of these discrete local times and understanding how their behavior depends on the dimension of the random walk. Okay, so just a couple of takeaways. So we've shown that the quenched density for the random walk and random environment has Gaussian fluctuations for all alpha less than 3/4. We showed that it has non-Gaussian for alpha equals 3/4. And okay, it's conjectured to have non-Gaussian fluctuations for all alpha greater or equal to 3/4, but this is actually an open problem. Our techniques work for any environment, not just the exactly solvable or beta case. And we're also able to explicitly compute the noise coefficient of the limiting model, which has a non-trivial form in terms of the invariant measure of the two-point motion. So some future directions. So the first one is what I just mentioned, which is actually to rigorously prove the Tracy-Whittem fluctuations for all alpha greater than 3/4. And then two natural generalizations that Shalin will talk about are, number one, what happens in higher dimensions, and number two, what happens if we consider more general diffusion models. So we've only been considering nearest neighbor random walks. What if you consider non-nearest neighbor random walks, or even maybe continuum models of diffusion in random media? So this will be the subject of Shalin's talk. And then finally, I just wanted to point out that there are some interesting physical applications to extreme value theory. So basically, what I mean by that is if you run many, many particles and you want to look at the behavior of the maximal particle, then the fluctuations of these maximal particles are governed by the same type of scaling limits that I described here. And this is interesting from a physical perspective and is the subject of ongoing experiments and simulations in the lab of Eric Corwin at the University of Oregon. Okay, so thank you very much. And if anyone's interested, I also included the references that you could look at later.
Thank you very much, Hindy, for the very nice talk. Are there any questions from the audience? Feel free to raise your hand or write in the chat and I'll unmute you. If not, maybe let me ask a question about the last slide that you were mentioning. So you mentioned
This
that
one
there
or
is
this one?
no, the open problem one.
Yeah.
So you mentioned that, okay, in the exactly solvable case for this beta random walk random environment, you can go to alpha equal to 1. This is open for other models. Can they go all the way from alpha to 1 to 3/4, let's say, at least in the exactly solvable case?
I see. So my understanding is, as far as I know, the only case that has been written out is the one by Ivan and Guillaume, which was for alpha equals 1 and for the beta random walk and random environment. I would imagine that it's not that hard to do it for the beta random walk and random environment for other alpha, although I don't want to say for sure. I mean, I haven't tried it. But for the beta random walk and random environment, you can exploit these exact formulas. So I would imagine that that would be more doable. And I think for other environments, it's really hard to prove, these tracy Ewing fluctuations, because typically, the known proof methods do really involve these integrable formulas. But as far as I know, I don't think anything has been written for this, even for other alpha for the beta case.
I see. Let me see. Any other question? Meanwhile, I can also ask. So, in your proof, you cannot really. I mean, do you have some understanding, at least some heuristics that you can do by going from a perturbative regime at alpha 3/4 to go a bit above that? Like you see, or you just see, okay, that this local time somehow goes up, and you cannot really.
Yeah, we
recently
haven't tried
try-
something like that. I'm not sure. I mean, maybe it's possible to do something like that, but we haven't tried that.
I see. Any question? If not, okay, let me maybe just, you just mentioned it at the very beginning. So the static case, so this CNI random walk, I'm not familiar with the literature. I mean, similar phenomena have been studied for the static.
So that model behaves quite differently. I'm also not an expert, but my understanding, I mean, the key difference with that model is that you kind of learn from the past. So if the environment pushes you in one direction in some location, then you can kind of get trapped there, because every time you're at that location, you'll kind of be pushed in the same direction. So you can imagine traps forming. So it really has this non-Markovian structure when you look at the annealed motions. So it's quite different. I know for those models, people care about like central limit theorems and invariance principles, but I don't know of anything analogous to this, like these kind of KPZ scaling limits, but I'm not sure. Maybe that it's possible to take a different type of
Okay.
scaling.
So there's only the Gaussian regime itself.
Yeah, but here, yeah, but that model is quite different, right? Because you really have that non-Markovian behavior in time.
Okay. It's clear. Thank you.
So I think someone's raising their hand, or maybe that's...
Yes. Cool. Yeah, I just allowed.
Hi, can you hear me?
Yeah, hello.
Thank you for the nice talk. Could you please elaborate a bit on the extra mass at zero for the infinite invariant measure of of the difference of the random walk? What is that exactly?
Right. So, this is something, okay, so let me just go to this picture. So the 2-point motion, I wrote here exactly what the transition probabilities are when the two random walks are together. So you can define the difference of R1 minus R2, and this is just a random walk on the even integers, I guess, right? And
Yeah.
if you look at this random walk, it should have an invariant measure. So I mean an invariant measure, like an infinite invariant measure in the sense of Markov chains. So you can just try to solve, for this nearest neighbor case, the invariant measure is actually reversible. So you could just try to solve the detailed balance equations to determine what the invariant measure should be. And it turns out that the invariant measure is constant everywhere except 0, but it will be larger at 0. So you have to choose some renormalization because the invariant measure is only unique up to renormalization. So suppose I decide to renormalize it so that it's 1 everywhere except 0, then you can compute that at 0, it's 1 over 1 minus 4 sigma squared. From this picture, from these transition probabilities. So it's really just solving the detailed balance equations for this random walk. In higher dimensions, it's more complicated and the invariant measure might not be reversible, so it might be harder to solve explicitly. But as Shalin will explain, there always is a unique invariant measure for these random walks up to normalization. So yeah, it's just something you can compute.
Would it be possible if your lattice is no longer discrete, say you consider random walk in random environment, but on the real line?
Yeah, exactly. So this will be the subject of Shalin's talk. So Shalin will explain, like for more general models, that we can also do a similar thing. So
Nice.
yeah,
Thank
stick
you.
around. That will be coming.
Thank you.
Thank you. Any further question? If not, if I may, maybe I have there is a small one. So you mentioned like about this appearance of this extra piece of variance. And you mentioned like okay, it's also something which appears in directed polymers in random environment, but in dimension, not in one dimension, but on
2 dimensions. Yeah.
Yeah. Can you elaborate more on this?
Yeah. So we'll actually see. So in Shalin's talk, we're going to study the 2-dimensional version of our model. So we'll actually see that in 2 dimensions, we have an even larger noise because we have both of those kind of phenomenon occurring simultaneously. I'm not sure exactly how much I can say. For the 2D directed polymer, you have the same phenomenon where the limiting noise also has a component that's independent of the pre-limiting noise. But my understanding is, I mean, they're kind of it's a similar phenomenon, but it happens for a different reason. So in our model, this extra noise is really coming from the stickiness of the random walks. So I think it's not happening for the exactly the same reason as the for the directed polymer in 2D. Yeah, I'm not sure. Maybe we could talk more about this later because it's
Yeah.
a bit difficult to,
Yeah.
start
Okay.
introducing the directed polymer.
No. Okay.
I'd be happy to discuss that after.
Perfect. Any other question? If not, I will propose to thank Hindy again for the nice talk and for answering all these questions. And I would suggest to maybe take a quick break of 5 minutes, and we start with Shalin. Okay. See you in around 5 minutes. Hi, Shalin.
Hey.
Nice. What time is it for you now?
10 a.m.
10 a.m. Okay, not too bad.
Yeah.
I don't feel so guilty for it. Would you like to try to share your slides so we see?
Sure. So let me try to share this one. This one. Yes.
Okay. Okay. We don't see it full screen, or we see it from the browser, something like this.
Okay. Let me try to present. Yeah.
Yeah.
Okay.
Okay. Now it's perfect. When you're ready, I introduce you and we can start.
Oh, okay. Sure.
So ready?
Yeah, I'm
Sorry.
ready.
Okay, cool. So let's restart the session of today with the second part of the talk. This time by Shalin Parekh from University of Maine, and the title is the same. And again, feel any question, feel free to raise their hand in the chat. So thank you, Shalin, for accepting the invitation, and please the floor is yours.
Okay, yeah. Thank you very much to Federico and Mariana for inviting us to give a talk here. We're very happy to be here. So this talk will be a sort of continuation of Hindy's talk, but I will try to make it as self-contained as possible. So the following model is motivated by work of Lejeune and Raymond from the 2000. So it's a more general model called stochastic flows of kernels. And throughout this talk, I'm going to let this I denote either integers or real numbers. If you like discrete things, you can think of integers. If you're more interested in continuous things, you can think of reals, and you really have the freedom to choose whichever underlying kind of lattice or continuum that you like. So a Markov kernel on this set I is a collection of probability measures that are indexed by points in I, okay, and Borel subsets of I. Now, I'm going to let M of I denote the space of all Markov kernels on I. And you can give that a nice topology, and therefore you can talk about random variables taking values in this space, M of I. And now in this talk, I'm going to consider a generalized model of random walk in random environment, which is defined by sampling independent and identically distributed Markov kernels from some probability distribution on M of I. Okay, and I'm going to consider the random walk in random environment that is determined by those Markov kernels. Okay, so just to kind of denote a picture of what of the model that I'm talking about. So each vertical line segment here denotes your underlying copy of I, meaning it could be integers or it could be real numbers. Okay, and now at each point of I, you have a probability measure at that point, okay? So imagine you start at 0, okay, the origin in space, and then you sample from the Markov kernel that is centered at that point, so k1 of 0 comma dx, then you land at some point x1, okay? And then wherever you land, okay, there is another Markov kernel which is sampled from the same distribution as k1, but independently, okay? And now you're going to sample a point x2 from k2 of x1, comma dx, right? And then you keep doing that. So when you land at x2, wherever you land, you know, there's a probability measure there, k3 of x2, comma dx, and you keep sampling in this way, and in this way, it generates a random walk in a random environment where you always move forward in time, and spatially, you're always situated somewhere on this lattice I, okay? So this is my model. And this generalizes the earlier model of random walk and random environment from Hindy's talk. Okay, and now the question of interest is to figure out how all of the exponents and coefficients generalize. So remember from Hindy's talk, we had some n to the 3/4, and then there was this strange coefficient, which was 8 sigma squared, 4 sigma squared. And the main problem that I want to discuss now is, well, for this much more general model, you know, what forms do these quantities take? Okay, so is the model clear, or are there any questions about it? Is the problem clear?
For me, yes. The audience does complain. So.
Okay, so that's our model. Now, of course, at this level of generality, we don't really expect a result. So we need to put some assumptions on these Markov kernels. So what assumptions do we need? Okay. So I'm going to look at the deterministic measure, which is given by the expectation of the Markov kernel centered at the origin. And I'm going to assume that that measure has a finite moment generating function, or at least finite in some neighborhood of the origin, okay? And I'll also assume that it has mean 0, but that's not really a real restriction. Okay. I'm going to assume symmetry up to order p, okay? So I'm going to assume that the first p minus 1 moments of k1 of 0 are deterministic, okay? But the pth moment is genuinely random, okay? So here p is just some natural number. And then the third assumption is, you know, we already said that these KIs, these Markov kernels, should be independent and identically distributed. But we also impose that K1 is translation invariant, okay? And moreover, it has rapid spatial mixing in total variation norm, okay? So there's a precise like inequality that I could write here, but it's kind of intuitive, meaning like if you look at the two kernels that are far apart, then they're roughly independent. And then the final condition is a technical condition that I'm going to impose, which is that this 2-point motion, which is defined as the expectation of this product, should define what's called a Strongfeller and topologically irreducible Markov kernel. And what this means essentially is that we want to get rid of situations where we might have absorbing states in the 2-point motion, okay? So Hindy discussed an example, which was the Bernoulli case of her random walk in random environment. And in that case, the 2-point motion, it has an absorbing set along the diagonal of Z2. And we don't want absorbing sets because they kind of ruin everything, okay? Okay.
Sorry, can I ask you just to about the second condition? Could you you explain this further? Like, so really taking like the probability of going from 0 to A, if I take any p power would be, and this should be deterministic for all A. Can you?
Sorry, what I mean is that this K1 of 0A defines a probability measure, right? A random probability measure. But I'm imposing that the mean of that probability measure, say, is deterministic.
Okay.
And then P would be 2, for example. If the mean and the variance of that probability measure are deterministic, then P would be 3, for example.
Okay.
And I'll give specific P values a little bit later. Yeah.
Perfect. Thanks.
Okay, so these are the assumptions on our Markov kernels. And now we have the main result. So we're going to let P omega of Tx denote the transition probability at time t of the random walker started from 0, given the environment. Okay, and here the environment is the collection of kernels, for all time. So the theorem is as follows. So we're going to define un of Tx to be some deterministic family of constants times our quenched transition probability evaluated at time of order n. And we're going to look now at spatial locations of order n to the 1 minus 1 over 4p, okay? So, if p is 1, then this is n to the 3/4. If p is 2, then this is like n to the 7 over 8, right? And, the CNTX, I have not written it here because the expression is kind of complicated. Just, you saw in Hindy's talk, but it's just they're deterministic. There's no randomness in the CNTX, okay? And then the result is that this family of random variables UN converges in distribution in this space to the solution of this multiplicative noise stochastic heat equation, which is also known as the Hopf-Cold transform of the KPZ equation, okay? Where the initial data is a Dirac at the origin, okay? And this gamma is a real number, which I have not told you what this gamma is, but kind of complicated. Just based, remember from Hindy's talk that the gamma was kind of like square root of 8 sigma squared over 1 minus 4 sigma squared, okay? So that brings us to the part 2 of our result, which is describing what is this gamma. So to describe gamma, I'm going to define what is called the gap process, okay? So as always, I will denote either real numbers or integers, and we are going to consider the Markov kernel on I, which is defined as kind of the difference of the two coordinates from this 2-point motion, okay? And we're going to let pi inv denote the invariant measure of that Markov kernel. And this is going to be an infinite measure, right? So in Hindy's talk, she kind of explained, well, when I is integers, typically this will be kind of like a counting measure, but with some extra mass near the origin. Okay, so now in terms of this gap process, we can express the coefficient in the limiting stochastic PDE as being equal to this following integral formula with respect to the invariant measure, okay? And the integral is kind of like, you can think of it as the variance of the pth moment, which is what appears in the integrand, and then you integrate that against this invariant measure for this 2-point motion, okay? So it looks kind of complicated, and I don't have a good intuition as to why you get this formula. It's just that you write things down very carefully, and you see a specific function popping out, and it's this function in the integrand, and that's kind of what you end up getting as the limit. Okay. And then you can check that if p equals 1 and our model of random walking in random environment is exactly Hindy's model, then you can directly check that this thing is equal to 8 sigma squared over 1 minus 4 sigma squared. Okay. So this was our main result.
Sorry,
Essentially, it says that kind of you have a universality statement for stochastic PDE, but this coefficient gamma will depend on the model, and this is exactly how it depends on the model. Okay. So
sorry, Shalin.
yes.
There is a question from the audience, which I will now. Andre, I think you can ask the question back.
Yes, thanks. You hear me?
Yeah. Yes.
Thanks. Just shortly, in terms of the moment that you described for the problem, that you have p minus 1 deterministic and the final bit is random, would it be possible that the moments would not exist, just theoretically? And what to do if the moments would be inexistent? Thanks.
The reason that the moments will exist is because we assume that this mu has a finite moment generating function. And you see, if the expectation of this thing has a finite moment generating function, then K1 itself with probability 1 will have a finite moment generating function as well. Now, that is an interesting question to ask. What if we don't assume that this moment generating function is finite? And in this, expect that this theorem will fail. Like in some sense, that corresponds to long range jumps, right? So if you have long range jumps, then instead of a Laplacian here, you might expect some kind of fractional Laplacian, or even some other kind of non-local operator. And then I don't know what the result would even look like in that case. It would be pretty complicated.
Thanks. Thanks a lot.
Yeah, maybe since we are here actually on the previous slide, so the coefficient that you need to, the exponential factor that you need to go up with C and T of X will not depend on P. I mean, doesn't have any.
It will not depend on what?
On P.
This P?
No, the critical moment.
Yeah, the CNTX, yeah, it will depend on P, I think.
Will depend on P. Okay.
Yeah, but I'm kind of thinking of P as like being a constant. I've suppressed the notation. Yeah.
Okay. Thanks.
Yep. Okay, so that's our result. Now, specific examples of models that fall within the framework. So, the first example is, the model from Hindy's talk, the nearest neighbor discrete random walk in a random environment. And in this case, you would choose I to be the integers, and then your value of P would be 1, because your transition kernels don't have any deterministic moments. I mean, the 0th moment is deterministic because they are probability measures, but the first moment is already random. Okay. Okay, now if you like, what you can do is you can look at the following stochastic PDE, which is a heat equation together with this conservative forcing, where V is a smooth in space Gaussian field and white in time. Okay. And then you can define your kernels according to the propagators of that equation. Okay. And here you would take I to be real numbers, and P would again just be 1. Okay. So most interesting models that are actually physical will have P just being equal to 1. So that leads to the question, what is an example of a model where P is not equal to 1? Okay. So here's one example of such a model. So at each lattice site in space and time, discrete space-time, you sample IID, uniform random variables, U of t comma x, okay? And then you impose that these probability kernels k t of x will jump in any one of three directions, up and right, straight, or down and right. And you enforce that they have respective probabilities, 1 minus the uniform divided by 2, then the uniform, and then 1 minus the uniform divided by 2. So then you see that of this kt is deterministic, right? It's centered at that base point x. But the second moment will be genuinely random. So here, this defines a model with p equals 2. Okay, so a fourth example, which I think is very interesting, is called sticky Brownian motion. This is what's called the black noise, in the sense that there's no underlying IID weights or Gaussian forcing, but you still have a description in terms of these kinds of stochastic kernels. Okay, so these are examples of models. Oh, and a fifth example, which was studied by Barakand and Cassini recently, is is the KMP model, the Kipnis, Marchioro, and Presutti model. Okay, so just some more intuitive explanation and context. So there's a generalized interaction that we allow for these kernels, where you no longer assume spatial independence. So our model allows spatial correlations of different kernels. So you don't, your invariant measure for the 2-point motion now is not necessarily just has extra mass at the origin, but it can have extra mass at other lattice points too that are near the origin. Okay. And now the drift term to describe the KPZ scaling is given by n to the 4p minus 1 over 4p, right? So when p equals 1, right, you do get the n to the 3/4. For p equals 2, you get n to the 7/8. And then you see there's this whole sequence of exponents that describes the KPZ crossover. The noise coefficient of the limiting stochastic PDE is given by some value that can be described in terms of the 2-point motion or gap process generated by these stochastic kernels. And then, the result includes many different kinds of models. And the discrete time setup also includes continuous time models, as we saw with that stochastic PDE example, right? So just take the family of propagators and evaluate it at discrete time intervals. Okay, now some results in higher dimensions. So it's kind of clear that this stochastic kernel model generalizes quite easily to higher dimensions. So now our lattice I, which was either integers or reals, now you have some freedom. You can take it to be RD or ZD, right? But the actual details of the model are described in exactly the same way, okay? So instead of lines, now you can have planes or, higher dimensional Euclidean spaces. So here's kind of a brief summary of what Hindy and I have been working on in these higher dimensions. So similar to the n to the 3/4 location scaling to observe the transition in one dimension, you can observe a crossover at locations of order n over square root of log n in dimension 2, okay? and locations of order n in dimensions 3 and higher, okay? So this should say D greater than or equal to 3. And we'll see that in higher dimensions, you see that there are kind of more regimes where you can see Gaussian fluctuations. And I'll explain what that means in just a second. Okay, so let me describe for you more precisely our results in higher dimensions. So in higher dimensions, it turns out that you cannot start from a Dirac mass at the origin, meaning your random walkers are not all allowed to just start from the same point. And the reason for that kind of becomes clear at the level of the stochastic PDE limits. So if you look at the following stochastic PDE, which is given by this heat equation plus this additive forcing, where this G is just a deterministic heat kernel, then in dimension 1, at least formally, Hindy explained that the solution is given in terms of the Duhamel formula by this expression, okay? By this integral against the spacetime white noise. Now, in one dimension, there's no issue with this. So this stochastic integral will exist. And in fact, it will define a continuous function in both t and x. In higher dimensions, this is no longer the case, okay? And in fact, it doesn't even make sense as a tempered distribution if you allow distribution valued solutions. And the reason for that is that even if you try to smooth out this v with a test function, you have this g of sy here, and that is not a square integrable singularity in dimensions 2 and higher, okay? So we cannot look at Dirac initial data in dimensions larger than 1. So the question is, what kind of initial data can you look at? And so we consider a generalization of this equation where we still have a heat equation, but now instead of the GT itself appearing here, we convolve just spatially with some initial data profile, which is given by H0. And the question becomes, which class of H0 does the solution for this stochastic PDE actually exist? And because it's a simple additive linear, Gaussian object, you can answer this question quite precisely. So the optimal class of initial profiles, H0, for which a solution will exist, is things that have regularity slightly larger than -2, okay? And what I mean by this is you can look at distributions, but those distributions have to be controlled in some sense to have regularity -2 or better. Okay. So now, with all of this background, I can describe some of our main results in dimensions 2 and higher. So we're going to let omega denote our collection of kernels as before, okay? Then the fluctuations of your quenched density profile, if you center at location Dn, okay, is given by, well, there's several cases, right? It depends on how you choose this Dn. And I think Hindy explained in dimension 1 what some of these cases look like. So the first case is where your recentering location is of order n to the 1/2, okay? So then it matches the spatial scaling around the x variable. So in this case, it turns out that without loss of generality, you can just assume that Dn is the origin, meaning it is at 0. And then you have Gaussian fluctuations, but those Gaussian fluctuations are described by a conservative stochastic PDE, okay? So you have a kind of divergence of a vector-valued space-time white noise as the driving noise in your stochastic PDE. And you kind of expect this because you're looking at a conservative system, right? So meaning the mass of your quenched probability transition density is conserved as you evolve the time. Okay. The next case is where your distances dn are strictly larger than order n to the 1/2, but smaller than that critical scaling root of log n. And here we have Gaussian fluctuations again, described by an additive noise stochastic heat equation. But the difference is that now you do not have a conservative forcing. Okay, and the reason is that, well, multiplying by the CNTX destroys the conservativity of the system, right? You no longer conserve the mass. And then the third case is when you are at this critical scale, meaning you look at Vn times log n to the -1/2, where V has a small kind of radius. And here you still have Gaussian fluctuations. And the stochastic PDE that you see is quite similar, but now you see that your noise coefficient begins to degenerate. Now I've described these results, but I have not told you what this gamma hit is over here, or what this gamma of V here is, and likewise over here. So let me try to describe that soon. And these are the effective variance formulas. So recall that we have this 1-point motion, mu of dx, and the 2-point motion, which is given by the expected product of two separate kernels. Then we have these explicit formulas for gamma, small gamma of v, and for capital gamma, okay? And this is kind of what I was explaining earlier with the one-dimensional case, is that these formulas can be written as a sort of integral against the invariant measure. But now, because we are in higher dimensions, you see the appearance of this direction vector in your results. Okay, so kind of the takeaway from this result is that, well, you still have Gaussian fluctuations at this critical scale, and you still have these effective variance formulas, but they're kind of more complicated because they involve this direction vector. Now, you can, in this formula, you see that it doesn't actually cover anything beyond small values of v. So you see that here, the denominator will blow up exactly when gamma of v equals 1, okay? And now, what we expect is that if you zoom into that exact slope where gamma of v equals 1, then you should get some really interesting behavior. So you should see a non-Gaussian scaling limit called the 2D critical stochastic heat flow. And this is something that we are still actively working on with Hindy and with Jonathan Wang Ho. So I'll talk more about this later. Okay, so are there any questions on the result? Oh, yes.
Yes, anticipated. So if I remember correctly, in these results, I mean, there was also like this denominator also in the Gaussian regime, right? Here they don't appear because of the convolution.
Are you're asking about this?
Yeah, so okay. In the critical regime, you have a very similar structure, but also in the Gaussian regimes, you had, I mean, you expect somehow, okay, to have a degeneracy of the noise. Okay. So, yeah, in this, so she was always starting from a Dirac.
Yeah, I think you have a good point. So here, you should think of gamma of v as kind of being like the h sigma squared over 1 minus sigma squared. And here, you see that it's still like that. So you're performing that operation again. So it's kind of like an 8 sigma squared over 1 minus 4 sigma squared in the numerator, and then you also have that in the denominator. So you have like two instances of that operation.
I see.
So here you have a degeneracy which kind of goes beyond just the
I see. So it's a particularity of dimension 2. This
Yeah,
extra. Yeah,
this expression is a particularity of dimension 2.
I see. So I think there are other questions from the audience. Let me. Yes, Andre, please you can unmute yourself.
Can I have the question?
Yes.
Yes, thanks. So just shortly, you mentioned that this all takes place only on Euclidean spaces related to the lattice framework. Could this be also out of Euclidean or anything else? Thanks.
That's a good question. Yeah, I don't know if you would have similar results outside of the Euclidean regime. At least kind of. I don't have good intuition for that. Yeah, maybe you can have like similar results on like some hyperbolic space, but yeah, I don't want to make any guesses.
Thanks. It's okay.
Okay, so these are our results in dimension 2. And finally, let me talk about our results in dimensions greater or equal to 3. So in dimensions greater or equal to 3, you have kind of a similar story. Okay, so in the bulk regime, meaning if you scale your dn to be of order 1/2, you see this kind of conservative stochastic PDE with the additive noise. And then you have several extremal regimes. So the first regime is where this dn is strictly between n to the 1/2 and n. And there you again see an additive stochastic PDE, but it's no longer conservative when you're not in the bulk regime. Okay, and then there's this kind of critical regime where you are scaling like v times n with v very small. And here you see somewhat more interesting behavior. So you have an additive stochastic PDE, but instead of the usual Laplacian, you see some effective variance operator here, which is like the divergence of some matrix times gradient of W. And this matrix, it's just a constant matrix. It doesn't depend on like X or anything. And it's given by the Hessian of the log moment generating function of the one-step law at that vector V. Okay. And then you have some effective variance again instead of this gamma. And then this heat kernel here, it corresponds to the heat kernel for this operator. Okay. And in some sense, this is not so surprising. So let me just describe briefly what this effective variance, nu effective of V is, and why it's different than in dimensions 1 and 2, okay? So I'm going to take my two-point motion, and I'm going to define its exponential tilting Q by just defining the Radon-Nikodym derivative, which is given by this form, okay? And then I'm going to denote by this expectation, the expectation with respect to the gap process of this Q, the tilted two-point motion, okay? And then I have the following expression for my effective variance. It's kind of complicated, but the individual parts just consist of some kind of exponential functional integrated against the invariant measure for the tilted gap process, okay? And this exponential functional, you can explicitly describe this function u as the log moment generating function of the two-point motion minus twice the log moment generating function of the one-point motion, okay? So I know it's probably kind of not that clear because it's such a large formula, but in some sense, what I'm trying to say is that this effective variance in dimensions 3 and higher can be expressed as some kind of exponential functional, okay? Which is different than what we saw in dimensions 1 and 2. And notice here that this is not a polynomial function of V, which was the case in lower dimensions. Okay, so those are the main results. Let me say a quick word about the proof. So if you look at this quenched density and you multiply by those constants, C, N, T, X, it turns out that that solves a discrete stochastic PDE, which is of this form, okay? And this Ln is a discrete heat operator, okay? So it's some approximation of the usual heat operator, which might depend on your lattice, okay? And this M is a martingale, okay? So this is really the key idea behind all of our proofs. The results seem complicated, but ultimately you just derive some kind of equation for your quenched density. And then what you need to do is study the quadratic variations of those martingales M. Okay, now you can do some explicit calculations. And when you do the calculations, the quadratic variation of those martingales takes on the following form. Okay, so here t is time, phi is some kind of a test function. And now I have a huge expression, so let me try to break down the individual parts of this expression. So I have a time average, then I have an expected value with respect to the quenched two-point motion, okay? And inside the expected value, there are three terms. So here we have two copies of these constants, which you expect because it's the quadratic variation, so you expect kind of a second moment type of thing appearing there. And then you have these two terms, phi and f. Now phi, you see that there's this n to the minus 1/2 factor there. So you can think of phi as being kind of a global or macroscopic test function. And then you have this f, which is local, right? So there's no factor of n to the minus 1/2. So you can think of this f as capturing the local effects between your two random walkers, R1 and R2. Okay. So the phi can be a general test function, okay? But the f is some specific function, which kind of describes the interaction between two separate random walkers. Okay, to summarize, the quadratic variation of the martingales can be written as a quenched two-point motion of the following quantity, which is given by a product of these tilting constants times a macroscopic quantity times a microscopic quantity, okay? Now we're going to look at this Q, and we're going to look at its annealed expectation, meaning we're just going to take the expectation over the randomness of the kernels omega. Okay, so now take that expectation, and then you see you have an expectation of the quenched expectation. And now we're going to contract those two expectations. And when we contract those two expectations, we just have an expectation with respect to a Markov chain. The Markov chain is just the two-point motion that Hindy described in her talk, okay? And so you see now that the expectation of the quadratic variation is given by an expectation of that three-term product with respect to the two-point motion, okay? And now what we're going to do with this three-term product is that we're going to use these constants, and just as Hindy explained, we're going to use these constants to tilt the Markov chains, okay? So this two-point motion is a Markov chain. The CNTX, they define some Radon-Nikodym derivative. And now when you tilt, the key observation is that the tilted process is still a Markov chain, okay? And that's kind of a miracle of these random walk and random environment models. And now the product of those two constants is not a martingale because you have the interaction of the two coordinates in the two-point motion, but you see that it's almost a martingale modulo this cost functional that you get. And this cost functional is exactly a kind of exponential functional, where this f is some specific interaction kernel, okay, which is actually the same as this f. And then these exponential functions can be studied, but exactly as Hindy explained, their behavior depends strongly on the dimension. And this is ultimately what leads to the different behaviors in different dimensions as described in the previous theorems. Okay. Okay, so this is pretty much the end of the talk. Let me just describe some future directions. So here in our proof, we really use the martingale problem. We don't use polymers, but there seems to be a kind of obvious connection to the polymers when you look at the form of the results. And so one thing we're trying to understand is that why do these random walks in random environments behave like polymers? You know, what's the underlying mechanism for that? And so we're working on finding a kind of a bijection of sorts, such that, you know, the inverse temperature for the directed polymers could somehow be mapped to this gamma function for the random walk in random environment models. Okay. Then there's the question of, well, I assumed that I have some Markovian structure, right? So my stochastic kernels were independent in time. But what if you introduce some weak correlations between those kernels? To me, that's a very exciting problem, and I'm working on that right now. And I don't know what this gamma will look like if you have the temporal correlations, but I would like to understand that. And then finally, with Hindy and Jonathan, we're working on the critical case in 2 spatial dimensions, where you scale your gamma exactly in this way, and then you try to find the limit. And you know, the conjecture is that you get this critical 2D stochastic heat flow, which was recently constructed by Caravenna, Sun, and Zygouras. And we're working pretty hard on that. So these are kind of the main works in progress right now. This is just kind of some selected references that were kind of inspired our works. And it's not a complete list of references. Sorry if I didn't cite your paper. And yeah, thank you very much.
Thank you a lot, Shalin, for the very nice talk. Are there any questions from the audience? Alessandra. So, Alessandra, you could unmute yourself, ask the question. Then check.
Okay, do you hear me?
Yes.
Yeah.
So thanks for the nice talk. So this is my question. So your sequence of Markov kernels, so K1, K2, K3, so these are IID. But could you, so have you some ideas, I guess, in the case the sequence is a Markov chain?
If these Ki are a Markov chain,
I think that Bolderghini and other people consider also the case of environment evolving like a Markov chain, if I remember well. So that is okay.
Yeah, I've seen kind of the papers where they consider where distinct sites evolve as Markov chains, but distinct sites are independent. So in some sense, it's kind of opposite of what we do here. Here, I assume distinct times are independent, but distinct spatial locations may not be. And yeah, we haven't really thought about these KIs when they are just evolving in some Markovian way. But yeah, that could be interesting and like simpler than the general case of just correlated kernels.
Okay, thank you.
Thank you. Francesco, I guess you could unmute yourself now.
Do you hear me now?
Yes.
Okay. So it's mainly a curiosity. And Do you think that this kind of proof can be extended in the context of colored random walks? So imagine that you have like two types of particles that, for instance, share the same environment. What do you think this is possible? And in case, what kind of limit do you expect to have I mean, what kind of limiting equation do you expect to have?
Wait, what kind of random walks? Colored?
Yeah.
I'm not sure. I'm not so familiar with that model. Yeah, I think I need to do more research on that.
Okay, thank you. It was mainly a curiosity.
So if I interpret Francesco's question correctly, kind of starting with some colored mass, let's say in different locations of space, you have two masses, but different colors.
Yeah, exactly.
Correct?
So the
Yeah.
kernel, you have like, I don't know. Okay, it's like a
But
curiosity.
you applied.
Yeah, like you have two kernels, one for each color, and then this color at some point, for instance, can share the same environment and have different interactions. I don't know, it's more like indeed a curiosity and something that could be done.
Different color. I'm not sure. Which observable would of that would you like to would be interesting to study? Like would there be some kind of quenched probability density for that as well, or?
Yeah, I mean, I would imagine so, but I cannot be very precise.
Oh, I have to look into it. Yeah, but thank you for the question.
Okay, thank you.
Any further questions from the audience? I don't see any. So I understand, I want to make sure, so you had this condition in the critical regime in dimension higher than 1 of the V to be small, no?
Yes.
And so really, so as Hindy explained, the problem is this moment generating function. So it's where you are blocked, and but you have some conjectures on how to pass this. It's a technical thing, or will you see something different?
So yeah, so V is it needs to be less than 1 because you definitely have some kind of denominator blow up at 1. Here we're not able to actually get all the way to gamma of V equals 1, and that's technical. So we expect to be able to, for the same result, essentially to hold all the way until gamma of V equals 1. But we can only get kind of gamma of V less than epsilon. And so, yeah, it's a technical thing, and it's exactly this issue of that the moment generating function of an exponential random variable has a vertical asymptote, and that you see this expression is exactly kind of that moment generating function. Yeah.
Mm-hmm. I see. But after that, I mean, after that, you expect the different rescaling will give you a limit. I mean, is this where you expect to have some critical stochastic flow?
Yeah, well, there are two questions. There's a question of where gamma of V is exactly 1. And that's what we're working on with Hindy and Jonathan with the critical stochastic heat flow. And then there's the question of what about, well, gamma of V larger than 1? And that's the supercritical case. And that supercritical case is basically completely open. And I think even the physicists and even people who work on polymers kind of I think there are very few guesses. At least I don't know what should happen there. So in dimension 1, there's a clear guess, right, that you should get this directed landscape. But in higher dimensions at supercriticality, it's much less clear, even what the guess is. Forget about, rigorous mathematical results.
Mhm. Nice, nice. So, are there any other questions from the audience? I see some raised hands from Alessandra and Francesco, but I'm not sure whether this is still from the past or new hands. In case, please ask the question. Okay.
Do you hear me?
Yes.
Okay. So have you considered also, so all your kernels are have a zero mean? Have you considered the bias case? That is, so the case of random walks with bias, so a drift, and so the kernel have so not necessarily zero mean.
Yes. Here, if you have mean m, the only change in the result would be that here, instead of n to the 1 minus 1 over 4p, you would see that m times n times t plus n to the 1 minus 4p times t. So the result would be quite similar,
Okay.
but you just need to kind of go in the right direction. And it didn't fit on the slide, so I just put mean 0.
Okay, thank you.
Yes.
Thank you very much. Final questions, I guess there are none anymore. So let me thank again Shalin and Hindy also for the very nice talks for today's, and thank you everybody for coming, and yeah, for the very interactive session. And we resume for the last seminar of this semester in half January. So this will be the next and final appointment for this fall semester, and that's it.
Thank you.
Thank you. Closed.
Okay, well, Federico, I just wanted to answer your question, I guess, now that people have left, just about the directed polymer.